It's my pleasure to introduce our last speaker of today, Marco Carmosino, and he's going to tell us about metapersonal view of average case complexity.
Yeah, so hello everyone. Happy birthday, Russell. Thank you very much for having me. I'll be giving this talk backwards in time. My time slot is listed as from 5:14 to 5 p.m. So I shall take that up with the organizers, i.e. my past self, using the time machine that they owe me in negative 15 minutes from now. So on that note, I'd like to discuss one of my favorite science fiction authors today. No, not that guy, but this guy. Russell has been able to shift paradigms and tell stories in a way that was personally transformative for my life, and indeed, I think, for our field as a whole. And I think that we can locate that in his alternative career in an alternative world as an author of very thoughtful science fiction. So let's begin. What's in a world? Like what's around us? Well, usually there's an upper bound, right? We have some assumption about a class of problems in computational complexity. We say, yes, that class of problems is easy. There's also generally a lower bound. We say, okay, there's some task that's difficult. And these two properties, both an affordance and a friction, define the world around us. And they're tied together by a story, which Russell fabricates. So here's our first world for, oh no, my little window is in front of our planet. There we go. So here's our first world for today. It's called Algorithmica. You can notice it's this kind of techno-planet over here, right? Let's fill in the world. So here's the upper bound, P equals NP. That's why the world is dramatic, coded in technology. You can imagine Trantor or perhaps Coruscant, depending on your taste in science fiction. The story is science fantasy. We might as well be wizards in this world because we can solve problems that are so hard in the worst case that seem intractable today. And the pros of living in this world are pretty great. Russell actually refers to them as Spock level estimates of probabilities in a paper that this talk is not about. This talk is about a personal view of average case complexity. You know, Russell's perspective, not some paper that he wrote a while ago. The con to living in Algorithmica is that we cannot keep secrets from each other. No more secret codes, which is too bad, I guess. We'll get to that later. Here's some. So I'll be giving a few stories in relation to these worlds as the talk goes on. I'll also try to give a little bit of a status update on some of them. For Algorithmica, the status update is that probably we can't prove P equals NP. It would be amazing if we could prove that we can't prove P equals NP in some reasonable fragment of bounded arithmetic, but that's an open problem for another day. Instead, I'd like to tell an anecdata about Russell. So the scene is 2015, University of California, San Diego. It was my research exam, which is one of the best parts of being a graduate student at UCSD. Instead of exams and quals, we write something, kind of a research report, and we give a presentation, and it's a practicum. It's pretty great. I wrote mine about the utility of computational hardness. Again, more about that later. And at the end I said, okay, so my to-do item for the end of this exam is we're going to try and separate X to the NP from BPP. And this can be seen as a very reasonable first step, so I thought, towards ruling out we live in Algorithmica. Russell said, it's good to have goals. I have not yet separated X to the NP from BPP. Neither has anyone else. He also said, you know, after a few years of working on this and related problems, do you want to learn about boosting, like maybe the hardcore lemma? And I think this is one of the best things about working with Russell. He told me that it's good to be working on problems that are probably too hard for you to work on, as long as you take something away from those problems, you chip off pieces, and you use the insights elsewhere. So I've been treating another paper that Russell wrote about the hardcore lemma, where I believe you're one of the inventors of boosting, at least a parallel development. That paper is kind of like a self-help paper, right? Because in a boosting algorithm, you look at what you've learned so far, you find uncertainty around you, and you concentrate it in the distribution of examples. So I guess we've accumulated 2 alternative reality authorship careers for Russell, science fiction and self-help through boosting. Okay. So now that we've got Algorithmica, now that we've got our first assumption out of the way, let's talk about how to manufacture more worlds from Algorithmica. What are we going to do? We're going to take the upper bound and we're going to negate it. This is pretty mechanical, right? Because we assumed P equals NP, we'll get P naught equals NP, that'll be fine. And then where do we go from there, right? We need to pair an upper bound with a lower bound to create a plausible story about the world. And we're going to use the story that we told ourselves about Algorithmica to imagine a new upper bound. So here's Algorithmica in flux. The new lower bound is obvious, but the new upper bound, let's take a look at this, this good part of Algorithmica, the fact that we are basically computational wizards. Let's make it just a little bit worse. Can we be computationally great, if not computationally awesome? And that comes to the question of how do we relax P equals NP? How do we get a lot of the benefits, but maybe not all of them at once? Maybe we don't ask for too much. So this again is a direct quote from a personal view on average case complexity, which this talk is not about. A problem could have no efficient worst case algorithm, but still be solvable for most instances or on instances that arise in practice. And a lot of what this paper did for me, at least, and maybe for many of us, I don't know, I was not working in complexity theory in 1995, despite my time machine, is it made Levin's theory of, yes?
You will be.
Yeah. Ooh. I'll tell my past self that presently. This paper made Levin's theory of average case complexity fun and easy to understand. So let's go through that. I'm going to let mu n be a distribution on n-bit strings, and then I'm going to have an ensemble of distributions. So this means that I give my distribution, I say, I want to think about examples of the following size. I want to think about 500 by 500 pixel images, or I want to think about audio tracks that are represented by 5 megabytes, right? This is easy. This is fun to get a hold on. And then we say that some mu is in psamp, polynomially sampleable time, if there's a randomized polytime algorithm A, such that for every size of the artifact that I could desire, when I give it that size, it exactly replicates the probability of the ensemble. And Manuel and Russell were talking today a little bit about the philosophical content or interest in theoretical computer science. One piece of that is saying, let's carry out the thought experiment that our world is tractable in the sense that the natural phenomena we see around us, let's try believing that they're polynomially time sampleable, that nature is efficiently generating stimuli for us. Okay, so now that we've got psamp, a computational bound on the world around us, we say that a distributional problem is a function f and an input ensemble y. We're evaluating that function on the ensemble. And we can relax NP to dist NP, the distributional problems where there's a function in NP and a distribution that's efficiently sampleable. Okay. These are also words that Russell used in a personal view on average case complexity to describe his personal view on average case complexity. He said, some researchers may think that I am clarifying and amplifying existing work on average case complexity. Other researchers may think that I am confusing and complicating that work. So here we see that not only is Russell a master of win-win arguments in theoretical computer science, but also in rhetoric. There's, yeah, that's a full case analysis of reactions to the paper. And then he goes on to say, as this is basically a propaganda piece, I will present my own personal view of what makes the field exciting. And this is a lot of why the paper is so fun to read. He uses vibrant and entertaining language. I think at one point, you also call the proof of something messy and stupid. We'll come to that in a moment. But yes, okay. So now let's get the upper bound class. And I actually want to give this in a little bit of detail because it's cool. To compute f with benign faults, and this is exactly the language from personal view. That means you either output a question mark or f of x for all x. You know when you're wrong if you have benign faults. And a polytime benign algorithm scheme, I guess don't pay too much attention to the details. It runs in time poly x, so the size of the thing you're asking it about, and 1 in delta. It computes f with benign faults, so it always knows if it doesn't know the answer. And it's got this trade-off, right? You can give it delta, and you can say, okay, spend more time so you can be more sure of giving an answer. And this was apparently the part of, I also read pieces of Levin's theory. This trade-off is what's easier for me to read and understand in this definition than in the expectations over different polynomial exponents earlier. And I also like the phrase benign faults. Okay. So there's that definition, and here's the theorem with a messy and stupid proof. A distributional problem f mu is an average p if and only if it has a polynomial time benign algorithm scheme. And this was just manipulating Levin's definition and this definition and showing that they line up in personal case and average case, personal view on average case complexity. And I read through that proof a couple of days ago, and it was actually quite fun. So now I'm going to do it for, no. I'm not going to do that. My point is, we now have the tools to put Algorithmica in flux and go to our next world. So imagine wavy science fiction lines on the screen. Our new lower bound is obvious. We take P versus NP, we negate it. Our new upper bound is we're going to say, okay, maybe we can't compute NP in the worst case, but we've at least got distributional algorithms for NP. We've got heuristics. So it's pretty great. And this brings us to heuristica. You'll notice it's the same kind of technoplanet because they're not that different. It's just lacking some shiny doodads that Algorithmica had. Our new upper bound is dist NP is contained in average P. Our new lower bound, but P not equals NP. This is still a pretty aggressive genre of science fiction. This is space opera. You can get a lot done. You can have interstellar empires. You can have robots. A lot of Isaac Asimov stuff lives in heuristica. It's pretty good. And of course, the pro of living here is computationally. It's pretty great. The con is there's no more secret codes with a question mark because I don't understand the relationship between heuristica and cryptography yet at all. And we have difficulty with adaptive queries to these algorithms, right? Because on fixed distributions, that's where we have our guarantee of being awesome. But if we want to repeatedly solve NP-hard optimization problems, maybe that adaptive algorithm concentrates where we're not so good at solving these problems. I don't know. Okay. And what's the status of heuristica? So here, instead of telling a silly personal story about being a graduate student at UCSD, I'm going to give you some real technical content. I'm going to tell you that the very existence of this world is under threat. And to do that, I'm going to have to define, bear with me, please, the most classical and important and well-studied and well-known NP-complete problem you could possibly imagine, the partial minimum circuit size problem. This talk is also propaganda for the meta-complexity program. Okay, here's the definition of MCSP star. As input, you get the truth table of a partial function. So it maps n-bit strings to yes, no, and I don't care, represented by a star. You got a number, S in the naturals. And as output, you just have to say yes if there exists a circuit with at most S gates that agrees with F on all the Boolean values, and it can do whatever you want on the don't care values. Extremely recently, Hirahara proved that MCSP star is NP hard in 2022. And that is very exciting because, oh yeah, another comment on time travel. I think Avi said something about you all know what these worlds are at the beginning of the day today. So I'm here at the end of the day to tell you in painstaking detail what each world is. Yes, so this asking about the version with stars, without stars, the total function version, it's still open. And it's one of the most exciting open problems in complexity theory today. Yes, Russell?
And maybe you're about to say this, but this is the problem that Leonid was trying to solve.
That's exactly what I was going to say. This is the problem that Leonid was trying to solve, that he was talking about this morning, that delayed publication of his theory of NP completeness. Because wait, I gotta wait until I have problems that people care about the most, like the minimum circuit size problem. Okay. So yeah, fantastic theorem about this problem. So this problem is a classic. We just don't have the same kinds of hardness results about problems like SAT and three coloring, et cetera, until very recently. Okay. So why does this threaten the existence of heuristica? Well, okay. Shuichi Hirahara proves a lot of things. And one of them is that in heuristica, gap min KT, this is a party, so I'm not going to define resource-bounded Kolmogorov complexity, but you can think of it as related in spirit to the minimum circuit size problem. In heuristica, in this world, this version of resource-bounded Kolmogorov complexity is in P, which is amazing. But unconditionally, gap min KT star, the version of the problem with don't cares is NP hard. So all you have to do, quote, all you have to do to blow up heuristica is reduce gap min KT star to gap min KT. Get rid of the stars in this problem. Find a relationship between these two compression problems. And I'm not going to speculate on how likely this is to happen anytime soon, but it certainly seems like the existence of heuristica is more tenuous than it was before this pair of results. And that's very exciting. It's a plot twist in science. So now we're going to play the same game as before. New lower bound, obvious. Negate dist NP versus average P. New upper bound. I'm trying to reconstruct what Russell was thinking about here, and I'm going to speculate wildly and see if I'm anywhere near right. What if hardness is useless, right? Like, what if computational hardness abounds, but we can't use it for anything worthwhile? So what I would guess is that Russell negated these results from Impagliazzo Luby 89, where they were able to show that one-way functions, or the inability to invert certain functions, are essential for cryptography. So what that gives us, it gives us Pesseland, okay? So here, the upper bound is that there does not exist a one-way function, i.e. there are distributional inverters for every potential one-way function. The lower bound is dist NP is not an average P, so we don't have great algorithms. The story is a science fiction dystopia. The pros here are limited. There's something called universal extrapolation, though, right? Which says that if there's not one-way functions, that's actually an algorithm for inverting any distributional problem that you want. That's a pretty powerful learning algorithm. We'll come back to that. The con, though, is that you can't do crypto and there's no fast optimization. So it does seem pretty bad. And I think I've heard Russell say that this is the worst of all possible worlds, thus Pesseland. I don't know if that's actually a quote from the paper. Yeah, the pestilent Pesseland. That's actually I should have pulled that out. So this is what I want to say about the status of, I don't know that it's really that bad. First off, Nanashima is able to show that if there doesn't exist an infinitely often one-way function, then you've got average case learning in Pesseland. Then in joint work with Eric, hi Eric, Antonina, hi Antonina, and Ramya and Manuel Sabin, we used exactly the reductions used for cryptography in this Impagliazzo Lupi paper to show that if you have a natural proof, you get worst case learning over any distribution in PSAM. So this upper bound, these inverters for every kind of sampleable distribution, they're kind of good for learning. So Nanashima has this beautiful turn of phrase in his average case learning paper, can we terraform Pesaland? And I think that's a fantastic research program that everybody should be excited about. And maybe the take home message is that Pesaland is pretty bad for cryptography, but maybe it's amazing for learning, at least in the average case. Who knows? And why the negative spin, Russell? It's your third writing campaign as a propagandist. So yeah, new lower bound, obviously, we negate what we've got. There exist one-way functions now. What's the new upper bound going to be? So the story here is, what if one-way functions are everything? What if that's it from crypto? That leads us to the next world, which is this the kind of little desert planet, I guess, because it's livable, it's okay to be here. Minicrypt. The upper bound is in quotations here because I actually don't know how to phrase it properly. I don't really know how to give a complexity theoretic upper bound equivalent to there is no public key crypto, but maybe I could say something like factoring is easy, right? I don't know. But the lower bound is clear. There exists a one-way function. And the story is kind of cyberpunk, right? Like, and the pro is that a panoply of secret key crypto exists and is great. All of those protocols from their paper and further work in this world. The con is that there's no public key cryptography and there's none of these universal fast optimization and learning things that we saw from previous worlds. So we lose the universal extrapolation powers from Pesaland. And I don't know, that makes me feel a little bit better about Pesaland than Minicrypt maybe. I don't know. What's the status of Minicrypt? It's crisp. It's a crisp world in the sense that one-way functions really characterize what you can do here. They're kind of a complete primitive. And that emerged in Russell's work with Luby in '89. But even more recently, we see that there exists a one-way function if and only if K-poly, another one of the zoo of meta complexity problems, is mildly hard on average. You and Pasa are responsible for that. Hi. One of them is here today. And this is really exciting to be able to characterize the existence of these primitives with a precise problem that has been studied since the beginning of computational complexity. So to me, that makes Minicrypt seem like a crisp world with well-defined boundaries and capabilities. So let's switch it up. The next lower bound is there exists public key cryptography. There has to be some hardness for that to happen. I don't understand the structure of it. What's our new upper bound going to be? I genuinely don't know. I don't know how to express an upper bound for the next world that's coming up. Maybe it's just empty and the upper bounds are everything that we can prove works today. But we get to cryptomania and it kind of looks like where we live, right? Hopefully it's habitable. So the upper bound, again, I don't know. The lower bound is that there's public key cryptography as some source of hardness. The story is it's just more cyberpunk stories. I don't know if you've read anything by Neil Stephenson recently, but it begins to seem more and more like a hard-hitting realism. The good thing is that we're amazing at selectively keeping secrets. There really is something magical and exciting about public key cryptography. And the con is, well, you know, look around you. This is the world that we live in. It has problems too. Okay. Here again, I'm going to have a quick anecdote instead of anything real to say for reasons that will become clear shortly. So when I did my research exam here at UCSD, it was called The Utility of Computational Hardness. And it was about de-randomizing uniform algorithms. That was mentioned by Avi in the first talk. Well, that was the gap between, okay, we have assumptions about hardness for circuits, we get pseudorandom generators. From assumptions about hardness for Turing machines, we get pseudorandom generators, again, 10 years later, by treating those as special learning algorithms for hard functions. Very cool. At the end of the research exam, the faculty ask you, important questions about what you've done. Is Mihir here? No. Okay. Well, Mihir said, okay, so Marco, hardness implies that you can simulate these randomized algorithms deterministically. That's great. What else is it good for? So I said a few things. I said, well, the Markov chain Monte Carlo simulations are very important for many areas in science. And if you want to do efficient communication protocols, you often need randomness to get past communication complexity lower bounds. I'm pretty sure there's some synchronization algorithms that you really need randomness. And then I ran out of stuff to say. And we waited there for an uncomfortable amount of silence. And he said, Marco, what about cryptography? Don't we need hardness of computation for that? And I said, well, yeah, we do. And I added an entire section to the research exam document, and then eventually did successfully graduate from UCSD. So yeah, I didn't really appreciate cryptography until I started abusing Impagliazzo Luby with Antonina and friends to expand learning algorithms based on pseudorandom generators. A much more natural application for it. Yeah, so I'll just make two more points here. First, Rudich in 91 said he constructed relativized worlds that show it might actually be difficult to obtain a description of a primitive that summarizes cryptomania in the same way that one-way functions summarize minicrypt. I have actually talked to cryptographers recently, like Marshall Ball and Tal, and Marshall described cryptomania as kind of more of an asteroid belt than a world. Like there's a lot going on, there's a lot of richness, and maybe it just doesn't have that crisp structure that cryptomania does. Sorry, that minicrypt does. And there's a new world on the horizon. Maybe it's called Opfistopia. I'm not going to talk about that at all today. So, okay, what have we done? I'm going to summarize the talk and then make some further comments. We start with a formless void, then we assume P equals NP, and we get Algorithmica. A world where we are computationally superpowered wizards. We negate that assumption and we get heuristica. We're slightly worse at being wizards, but it's still pretty great. We make yet more. We walk this chain of assumptions about average case intractability of computation down to a world that looks like our own world. And I think that's why the paper is called A Personal View of Average Case Complexity, because each type of intractability is distributional. And Russell even says this in the paper and in numerous talks that I've watched to prepare for this talk, that depending on who you talk to, different communities almost live in different worlds. Like the SAT solver people think, we solve SAT, we do this. There's distributions of instances where DPLL plus conflict-driven clause learning and restart heuristics work amazing. And the cryptography people really, really want hardness to exist so we can play magic tricks over the phone with public keys. Where do we really live? I don't know. And what I've spent a great deal of time working on with Russell and other friends and colleagues is an entirely different style of assumption, right? We start at the top, and we still negate P versus NP, but the upper bound that we give isn't an upper bound related to average case complexity, right? We don't say something like NP is easy on average, even though it's hard in the worst case. Instead, we say something like, okay, P isn't equal to NP, and also the proof was easy in some sense. And that brings us to an entirely different world, which I refuse to give a number and am only going to call vapor world, where what is this like? The upper bound is that there exists a natural property. The lower bound is that P is not equal to NP. The story is much more speculative fiction, right? The pros of living in this world are that we can learn anything that's compressible from a friendly teacher that we can ask questions of. The con is, as per usual, when we assume these kinds of upper bounds, there's no cryptography. We can't keep secrets meaningfully. The status of this world is dubious, right? Because the whole message of the natural proofs paper for Asparov and Rudich is 97 is that if you had these types of proofs that P is not equal to NP, you would break all known cryptography. So if we believe in cryptography, we can't believe that we live in vapor world, right? Later, we wrote Learning from Natural Proofs together. This was me, Russell, hi Valentine, and hi Antonina. We showed that, okay, if you have a natural property, if you did all of the work to develop a circuit lower bound in this framework, you can launder it into a learning algorithm that asks a teacher queries and learns a small circuit. The interesting thing about this is that there are actually natural properties, maybe not for the most general classes of Boolean circuits, but for circuits like AC0 and AC0 mod. So we were able to get some learning algorithms out of this. So I mean it when I say that vapor world is speculative fiction. It's an extended thought experiment that helps us think through the following idea. To what extent is learning the same as compression? And this is work that I've continued with Russell and with other people since then, and that other people have been involved in. So, for example, there's a really nice paper of Helly Goldberg and Valentin Cabinets that says, if you want to learn from random samples, that reduces to one of these minimum Kolmogorov complexity problems that, again, I will not define because Leonid Levin kindly defined them earlier today, and this is a party. So yeah, it's random samples. So in this model, you get membership queries. So you've got a target function and you get to say, okay, on this point, give me the value of the function. On this point, give me the value of the function. In this model, there's just a polynomial time sampleable distribution. Yeah, well, it's pack learning with complexity bounds on the distribution. The distribution has to be efficiently sampleable, but that's still pretty amazing. So yeah, this speculative world is, for me, about trying to understand the relationship between learning and compression and characterize them by each other. Okay. And that's it. That's it for my talk. Thank you so much, Russell, for teaching me many things over the years, like how to do research, what the minimum circuit size problem is, how to be persistent and generous with uncertainty, and for a selection of, I think, 4 novelty t-shirts from a club in UC Berkeley. To wrap this up, I'd like to engage in a game. One of these images was generated uniformly at random. Do you think you can learn? Can you tell which one is compressible? Give me a show of hands for left side is random. Difficult, right? Yeah. So this is an 8 kilobyte compressed image of Russell and Impagliazzo, and this is 114 kilobytes of random noise. And on that note, thank you so much, everyone.